Welcome to part 3 of this video series. In this video series, I'm explaining how to use large language models in the web applications. In part 1 and part 2, I explained the design of the application and how to design the prompt template for the large language model and the response we are expecting from the large language model. We also looked into how to create the custom data and the same custom data which we will be using to fine-tune the large language model. In this video, I'm going to explain the process of fine-tuning using the custom data which we created in the part 2. So let's start. Okay, I'm in the Visual Studio Code and I'm going to explain the code which is used to fine-tune the large language model. So before we run any code, we need to install these packages. I can explain one by one what packages are needed. The first one is bits and bytes, and we use bits and bytes to quantize the model. So quantization is nothing but taking a larger model which takes huge amount of GPU and compress it so that it only takes less amount of GPU RAM. Next, we need transformers and the PEFT. The PEFT is used to train only subset of the parameters of the large language models. And one advantage we will get by using PEFT is we don't need huge amount of GPU RAM. We only need the GPU RAM for the amount of trainable parameters. Then we're gonna use accelerator, which is also provided by the Hugging Face, and the data sets, which is also provided by the Hugging Face, and 3 Python packages. In this cell, I have created a variable, and this variable holds the location of the custom data. I have created a custom data in the part 2, and let me show you the custom data. So this is the custom data which I will be using to fine tune my large language model. And let me show you how many rows I have. So I have 414 rows of the custom data. Okay, let me explain this cell. In this cell, all I'm doing is importing some functions and some classes. And let me explain what each function or class is used for. The first function which I'm importing is a load dataset, which is coming from the package called datasets provided by the Hugging Face. And this load dataset is used to load our custom data, or we can also use this load data set function to pull the data set from the Hugging Face. Then the second one, if you see here, I'm using LoRa config class and PEFT model class. I will explain in detail what these are, but these are mainly used to train the large language model using QLoRa and PEFT. And the other classes here, they are coming from the transformers packages. And if you see the first class, the auto model for casual LLM, this is used to load the model, whatever the large language model we want to load. This is used for that. And the auto tokenizer is used to create a tokenizer for whatever the large language model we are using to fine tune. And bits and bytes config, this class is used to create a configuration on how to quantize whatever the large language model we are using to fine tune. And the training arguments, this is a class where we pass all the hyperparameters, training hyperparameters, and this training argument is used to train our large language model. And finally, the SFT trainer class, which is provided by the Hugging Face, and this is the class which actually does the training process. So let me run this one, and let me run this cell and also this cell. And meanwhile this one is running, let me explain what this cell is doing here. Okay, so if you see here, I'm loading the dataset using the load dataset function which I have imported in here. So let me explain what this function is doing. This function, all I'm saying that the dataset format is in the JSON, and the where exactly the file is located. If you see here, the train dataset variable holds the location to my custom dataset. So that is what I'm passing here. And I'm just saying that this is for train. In this video series, I'm not going to explain the evaluation or test, but if you want to use data to evaluate, then you can pass here split equal to evaluate. But for now, for this series, I'm only using the train, which specifies that we are using this to train the large language model. Then there is a custom function here. Let me run this function, but I'm going to show you why this function is used later on. Then let me explain what exactly I'm doing here. Okay, if you see here, I'm creating a bits and bytes config. I'm giving instructions that load it in the 4-bit. So I'm using 4-bit quantization so that I can save as much as GPU memory. You can also load it in the 8-bit quantization. If you want to use it in 8-bit quantization, all you have to do is load in 8-bit equal to true. If you want to do it for 4-bit, load in 4-bit equal to true. And then I'm doing the double quant as true. And if you don't know what double quant is, let me show you what that is. So this is the Hugging Face documentation, and according to the Hugging Face documentation, if we use this double quant, then we will save additional 0.4 bits per parameter. So effectively, we are saving a little bit more GPU RAM during this training process. Then I am using NF4. Um, this is a precision type, and the latest precision type for the 4-bit quant is NF4. And then there is a D type, and I'm specifying that the D type has to be B float 16. B stands for brain, float is floating precision, and 16 stands for 16 bits. So the reason I'm using B float is because Llama 2 and the Mistral, which is built on top of Llama 2, both are pre-trained using the B float 16. Then I'm giving the location whereby Mistral uh, large language model is located. I have downloaded my Mistral here in this location, so that's what I'm giving here. Next, this line is used to create the tokenizer. Like I explained before, auto tokenizer is a class provided to us by the Hugging Face, and this class will create a tokenizer for us. And all we need to do is we just pass the model location, and based on the configuration file in this location, the tokenizer is created by this class. Right. Then usually I give this here, but for this demo purpose, let me comment out this so that you guys know why that is needed. Okay. And then here, if you see, what I'm trying to do is I'm actually creating, so I'm taking the data set, my custom data set, passing each row in the tokenizer, and then I am mapping it back to the trained data set variable. So, and I'm also batching them. So that's what's happening here. Next, if you see this class, auto model for casual LLM, this class is also provided to us by Hugging Face, and this class will help us load the large language model. And let me explain a few things here. This class is expecting the model name. Uh, it can be a model name. If it is just a model name, it pulls the large language model from the Hugging Face. But let's say you have downloaded the model in your local system, then all you have to do is give the path where you have downloaded. Just like how I provided the model name here to the tokenizer, I just provided the path. Same thing goes here. Then I'm giving device map is equal to auto. So we can actually provide our own device map, but here auto will do for me. In most of the cases, auto should do fine. And what exactly the auto does is it checks our resources. So let's say I have 2 GPUs, then it checks how many GPUs I have, and it will load the large language model in those 2 GPUs accordingly. Let's say you have only 1 GPU and your large language model does not fit in 1 GPU, then device map auto will make sure that whatever the layers needs to be offloaded to the RAM, it will be offloaded, and whatever parameters or layers needs to be loaded in the GPU RAM, it will be loaded in the GPU RAM. Then we are passing the bits and bytes config here. So this bits and bytes config is coming from here, if you see. And based on this configuration, I'm telling the auto model for casual LLM class that load my model in 4-bit quantization, do the double quant. The quant type would be NF4 and the D type would be brain float 16. So that's all for this, and let me run. So it's loading. Right. So the loading is done, and let me show you how the GPUs or how the large language model is loaded on two of my GPUs. So if you see here, the GPU 0 has around 2.5 GB and GPU 1 has around like little bit more than 3 GB. So the distribution of the large language model in two GPUs is determined by this class because I have provided device map equal to auto. Then this is the function which I was referring to, the custom function. So let me show you what it does, and I'll explain why we need this. So when I run this, all it is doing is it's taking my training data set and it is giving a bar chart, and that bar chart is telling us that some of the rows in the data set are only 1400 length, some are around 1600, and there are few of them, like I guess around one, two, or three, I'm not sure, but there are some around more than 1900 something. And the reason we need to know here is while training, it's always advisable that all the training data sets, all the rows in the training data set will have the equal or the same amount of length. So to solve this problem, we can either truncate it, but let's say you don't want to truncate it, you can put a padding to it. In my case, I don't want to truncate, I want everything to be there, so I will put a padding. And if you see here, this function is giving you the number of rows in the data set and also the highest length of the each row, and I see 1937. So what I would do is I would pad everything to the tooth so that we can get max length of 2000. Okay, let me explain what's happening in this cell, but before explaining, let me comment this out so you know that why I have to add this piece of code. So let me explain what exactly I'm trying to do here first. So if you see here, I'm taking this training data set, looping over this training data set, and I'm passing each row in the tokenizer, just like I did before. But there is something which I'm doing here is I'm telling that the max length should be 2000. If there is any row which is more than 2000, then truncate it. That's why it's called truncation equal to true. But I'm also saying that if anything which is less than 2000, then put a padding. And I have used batched equal to true just like before. Let me run this. But if you see, there is an error, right? And if you read the error, it says asking to pad, but the tokenizer does not have padding token. So that is the reason I wanna do this padding token here. So I'm telling that pad to the right hand side. Some large language models need left, some are right. So I'm using the Mistral, so it needs right. So I'm padding it to the right hand side. So now when I run this, after putting the padding, it works as expected. And if you see here, now all of them are distributed evenly because we are padding here to the max length of 2000, right? Okay, so let me uncheck these two and let me explain what these are for. So if you see here, this model dot gradient checkpointing enable, we have to use this because I will be using gradient checkpointing, which I'm going to explain later in this course. Then we have to prepare our model for KBT training, and if you see this function is coming from the PEFT package provided to us by the Hugging Face. And all right, so let me rerun this. All right, now This is a function which is provided to us by the Hugging Face. I found this in Hugging Face documentation. And what it does is when you pass a PEFT model into this function, it will tell us what are the total number of parameters for that model and how many parameters we are training. All right. So in the next cell, if you see here, this is where I'm creating LoRa config, and also I'm trying to get or print how many trainable parameters are there, and also I'm trying to get a PEFT model. So if you see here, this get PEFT model is given to us by the PEFT package provided to us by the Hugging Face. Then this LoRa config class is also provided to us by the Hugging Face. So let me explain what LoRa config class is. So the LoRa config class takes two variables, R and LoRa alpha. R is called rank. So the general rule of thumb is whatever the value you give R, you double the amount of R has to go into the LoRa alpha. So if I'm giving R equal to 8, I'll put LoRa alpha is 16. If I give R equal to 16, this one will be 32. This one will be 32. So, and what exactly R specifies? So uh, the more or the higher the number of R, the higher the number of parameters. The lower the number of R, the lower the number of parameters. So let me demonstrate that. So now I'm going to give 8 and 16 here, and let me run this cell. And if you see in this cell with R equal to 8, this is the number of trainable parameters, that is 0.18. Let's say 0.19. Now let me give this R equal to 32 and this one 64. Now if you see here, the trainable parameters are a lot. Before it was 0.19, now it's 0.75% of whatever all the parameters are present. So these are, you guys can change according to your GPU requirements or according to your use case. You can play with different values of R and LoRa alpha. So for me, I'll just put 8 and 16. And then we should also specify the target modules. So how do we get the names of these target modules? I usually do Google search. So let's say you cannot find this information in the Google search. There is another way to find the module names. Let me show you that. If I open the model, so let's say this is where I downloaded the Mistral-7b model. And if you see here, you will see a file called PyTorch model bin index JSON. If you open this, you will see all the module names here, target modules, K, O, Q, V, all these target modules. And if you go all the way down, there might be different one like gate underscore projection, up underscore projection, down underscore projection. Let me show you another example. Let's say you are trying to fine tune the Mistral and you want to find the module names for the Mistral. So just go to the place or location where you have downloaded it. You will see the same exact JSON file. When you open the JSON file, you should see the module names W1, W2, W3. They have K, O, Q, V. And if you go down, you might have something else. You might find some other um, module names. But this is how we find the module names. The bias, I used none. There are three possible values. For this parameter, let us look into those three possible values. Okay, if you see here, there are three possible values: non, all, LoRa only. And non-specific, if you fine tune an application, if you fine tune a large language model using non, what happens is whenever you use the adapter on the base model for inferencing, and when you remove the adapter, the base model will work the same as before you added the adapter. But let's say you have fine tuned with all or LoRa only, then this behavior is changed. Let me show you the documentation. If you see here, If all or LoRa only, the corresponding biases will be updated during training. Be aware that this means even when disabling the adapters, even you remove the adapters, the model will not produce the same output. So now you are effectively changing the base model. Even if you do not want the adapter, even if you remove the adapter, the base model behavior has changed now. So I usually use none, but there might be use cases for you guys to use all or LoRa only. You can try it out. Next, this function will give you the PEFT model, and all you have to do is pass the model which you have created using auto model here, if you see here, and then you have to pass the LoRa config, which which I just explained before. You have to pass this LoRa config and you will get the PEFT model. And if you pass this PEFT model into this function, you will get the number of trainable parameters. So let me rerun this again with 8 and 16. I'm good with 8 and 16. You guys can try with different values. So let's look into the training arguments. The next step is to determine the training hyperparameters. To set the training hyperparameters, we use the class called training arguments provided to us by the Hugging Face, and this is coming from the transformers package. The first parameter, if you see here, it's called per device train batch size. So let's say I have two GPUs, and if I put 4 here, which means my effective batch size would be 8, because on each device it would be 4, so it would be 8. If you have only one GPU, whatever you add it here, it's going to be the same thing. And the gradient accumulation steps, and this is where we use to reduce the amount of GPU RAM requirements. Let's say you want to do the training with the batch size 16, but you don't have enough GPU. So what you can do is you can put one here, train batch size per device as 1, and the gradient accumulation steps you can put as 16, which is equal to the 16 batch size. If you do this, your training process is really slow, but your GPU requirements are reduced as well. So that's the trade-off we have here. So for me, I'm using 1 and 4 here. Then the warm-up steps, you can put whatever the number you want, 10, 20, 25, 50. You can just play with it. And then the learning rate. It is advisable that you start off with very less learning rate. And most of the documentation I see, they start off with this number for whatever the reasons. Probably it works good. So I'm using this number. But the idea behind is the learning rate should be really slow, and I can do a separate video on why the learning rate has to be really low. If it is too low, it's really bad. If it is too high, it's also bad. It has to be balanced, and I see this value to be good because I see a lot of people using this and they're getting a good results. Then I'm just saying FP16 is true. Then logging steps. So I'm just saying every 25 steps, log it. Um, there are some logging steps which you can see every 25 steps, and one of the logging step is the loss function. So ideally we should see the loss function value decreasing. If it is decreasing, which means your training is going as expected. And the output directory, if you see here, this is the output directory to save the checkpoints. So while training, you want to save the checkpoints so that just in case if you cannot make it through the complete training process, or even if you went or made it to the complete training process, the final output may be not as good as the intermediate outputs. So you should take the checkpoints and then use those checkpointing adapters to make sure which one has better responses for your use case. So this output directory is for the checkpoints, but not for the final adapter. And then I'm saying I need maximum steps of 500. And I'm just saying just save total number of checkpoints are 2. I just need only 2 checkpoints. Anyway, more the checkpoints, it's hard for us to understand which one has better responses. So I feel 2 is good for me. Then I'm saying here that save steps at every 250. So I'm giving 500 max steps, and I'm also saying every 250 steps, save the checkpoint. Then I am saying this parameter load best model at end false, even though I said maximum save limit is 2 and save steps is 250, which means I will always get only 2 because maximum steps are 500. But let's say this is 500 but save step are 100, which means you're going to get 5 of the checkpoints, but you only want to save 2. So in this case, if you put load best model at end true, then it will try to pick the best model within those checkpoints. And number of train epochs 3, I'm just giving this parameter here so that I can show you guys that there is a parameter called num train epochs. But because I already gave max steps as 500, I really don't think this is relevant here, because the training process will go until 500. If you don't know what epoch is, let's say in my data set there are 100 rows, and once the training process completes all the 100 rows, then it's called one epoch. So 3 epochs is like go through the whole training data set 3 times. All right, but I'm saying here max steps 500, so this is almost irrelevant here. I'm just showing you guys there is something called epochs, name train epochs. Next, this is where you can pass the optimizer, and these are all the possible values of optimizer. I always use Adam 8-bit, paste Adam 8-bit. I tried with the 32-bit. The results between 8-bit and 32-bit, for me, I didn't see any difference. Maybe there are some use cases where it makes a difference. For me, it didn't make any difference, so I will go ahead with the 8-bit. All right, so let me run this. Yep. The cell is loaded. So we'll go to the next and final cell. So here is where the training process starts. And for that, we are using SFT trainer class, which is provided to us by the Hugging Face. And you have to pass few parameters, and they are straightforward parameters. Here you are passing the PEFT model, which we created here. In this PEFT model, we have passed our base model, and we also passed the LoRa config to create the PEFT model, and that is what we are using here. And then we are passing the train data set, and then I'm passing the tokenizer, and I'm passing the training arguments, which we created here, all the training hyperparameters. Uh, and that's all for the SFT trainer. And you can use this line to train. And if you see this line, it is just to silence the warnings. It has nothing to do, or it does not affect anything in the training process. In this line, I'm saying that once the training is done, save the adapter to in this location. All right, so let me run this and we'll show you how does it look like. So I'm running this cell where the training is happening, and if we see here, this is how the training is. Because I am logging every 25 steps, and because only 2 steps have done yet, you're not seeing any logs. So let me rerun with less logging steps. Okay, so I changed the logging steps to 1 so that I can show you guys how the logging will be. So because the logging step is 1, for every logging step, you will see the training loss printed. If the training loss is going down, which means it's a good thing, our training is happening as expected. So in this video, we have learned how to do the fine tuning using the custom dataset. And in the next video, I will show you how to use the adapters produced or created by this training process. And we'll do the inferencing. And we'll also see how we can format our response in such a way that our web application can use it. So that's it for this video.